Greetings, Qiskitters! Welcome to another installment of the 12 Days of Qiskit. We hope you're having a happy holidays, and it's my pleasure today to introduce my partner in crime, Luciano Bello, who is our Qiskit developer calling in from Zurich, Switzerland. I'm your host, Nick Braun, quantum researcher with IBM, calling in from Medellin, Colombia. We have a chat going on the YouTube today, so while everyone's logging in, why don't you tell us where you're calling in from today? We can see who's, well, I guess we're pretty much on the other side of the globe, Luciano. Let's see who's closest to us.
I guess I have some advantage with so many Europeans, but yeah.
Right, probably true. So what we're going to do today is, as you might have seen, we've had a lot of topics during the 12 days of Qiskit. So for example, we've built bots, we've talked about quantum error correction, we've run through tutorials. Yesterday I showed you the gift of dynamic circuits, and it's kind of getting more technical. So today, Luciano and I are going to pull apart the Qiskit Transpiler and show some of the new features of what it does. And loosely speaking, we'll go into this, much further. Transpiler is what's responsible for taking an abstract quantum circuit that you want to run and turn it into something that will actually execute on a physical existing backend. So in this sense, it's kind of like compiling that you might know from classical computer programming. We call it transpiling because it takes a quantum circuit and the output is still a quantum circuit. It is a place where Luciano and I spend a lot of time. It's a pretty rich area filled with lots of ins and outs and pitfalls and the like. So no one's really told us where they're from today. So maybe we can just go ahead and start getting started.
Okay. Yes.
So yeah, we're going to go through a number of topics with an overview of the transpiler, and then we'll go through what the pass manager is. So the transpiler executes a series of passes with some level of control flow. And then we'll talk about how we can modify these passes and the stages that consist of a number of passes, and go through how we can debug these, how we can create our own pass manager configurations, and how we can start using plugins. So I'll go ahead and I guess Luciano is going to share his screen. We're going to talk about an overview of the transpiler. So we kind of go through, in this case, it's called an input circuit and an output circuit. We're back on your Jupyter notebook.
Oh, sorry.
Sorry. Yeah, no problem. I usually call these like an abstract circuit and a physical circuit, because there's one that's kind of in your head, one you've scratched out or you've programmed up in Qiskit, and then the one you want to execute on an actual device. And there's a number of things that you need to go through. So the first one of these, maybe you could expand the basis gates.
Mm-hmm.
So basis gates are the actual gates that can be executed on the quantum backends, and that's because there's only a limited set of things that can be executed, because you want to do a bunch of calibrations to make sure that you can perform the base gates that you can. And so you can only do that to a finite set of gates. And all the other gates that you're used to, say like a Hadamard gate or a Z gate or an X gate, those are going to be transpiled into their equivalent circuits. So they will be quantum mechanically identical, but they'll be converted into something else that has been calibrated on our backend. In particular, for our IBM backends, our basis gates are at the square root of X, which is a 90-degree rotation about the X-axis, an arbitrary Z rotation, and C naughts. And I guess we have X gates are in there as well. In addition to other instructions such as resets, measurements, the if-else statements I was talking about yesterday for dynamic circuits. And you can actually manipulate these and add to them and change them if you like, and that's another fun thing you can play with. But for now, we're just going to stick with basic gates. So as we can continue the next one.
The reason why we have X gate individually, I mean, an X gate is covered by it's a special case of the CX, right? But the reason why we have it individually is because it's easier to transform to a full base than assume that have this special conversion. Otherwise, if we have an X, we have to convert it to a CX, and that wouldn't be efficient. That's why we have it explicitly here.
Yeah, actually, the X's are used for dynamical decoupling. So So if you pull apart the C knots, you'll see that's where the X gates are used in the backends.
You pull apart
yeah.
the C knot. Oh, I see. Yes, yes.
Right. So and if you do dynamical decoupling passes, which is something else you can do with the transpiler, that's a pretty advanced usage. You can attach the X gates, for example, because you usually want to do those in terms of the full rotations. But that's like a whole thing I don't think we have to worry about. But you can see like, so these Hatta marks here and this phase gate here, this will eventually be, the technical term is unrolled into the basis gates. So you can probably see on the next, scrolling down, oh yeah, now everything is expressed in terms of X gates, square root of X gates, RZ gates, and C knots. So this is something that now,
given a transpiler, it takes the backend basis gates and transform to those ones. Yeah.
Exactly. So you can get all the information. You don't need to know the information. The transpiler will generally take care of all these things for you, and you don't have to think about it. But Luciano and I like to think about it.
Yeah.
I don't think we need to keep. We could just go to the next section.
Initial layout.
Initial layout. Right. So, superconducting qubits are, a planar type of architecture, which means it's very difficult to connect all of them together. So you typically have some sort of nearest neighbor type graph. But you have quantum operations that you might want to do between a lot more qubits. So you have to figure out how to best map those qubits. And I would say mapping consists of two parts. I usually call it routing, which figures out how you need to swap the quantum information around in a topology, and then layout, which selects the actual physical qubits you have on your device. And then these are things we'll talk about, I think at the very end when we do a plugin for a certain kind of mapping procedure.
Yep.
Anything you want to add about that?
Yeah, no, that basically the initial layout is the way that we allocate this. Well, if this one, you call it abstract circuit, right? The one on the left. So we can call them, I guess, abstract qubits, the way that they are mapped into the physical qubits. And yeah, you can control how to do that, and that will have an effect in the transpilation process.
Exactly. And being able to control that being able to control these things very well can eliminate redundant gates that you don't need to do, which can introduce error. So the better you can do all these steps, the better you can get the results you want out of the quantum backend.
Correct. Yeah. Okay, and let's go through the next stage, the routing, which I think maybe it's this one. Yes, I guess you're right.
So they're calling. Yeah. So this is selecting qubits, and then this is doing the swap. I think I like to think about it in the opposite order, but you kind of need to know a bit about both when you do this. So this will swap quantum information around after you've selected a set of physical qubits, and you can select these physical qubits based on their properties. So you can have, say, for example, information about their coherence times, information about their gate errors. Usually, what I'll look at is the C naught error, because that tends to be the one with the largest error.
Yep.
But there's different ways of picking qubits.
Also, we could already jump into code to show exactly that choice by errors that you describe, if you want.
Sure. Okay.
So let's do that. Unless we can take our example from here. So this is a special circuit, right, Nick?
This is like a 5-state GHZ circuit.
Okay, I hope the audience gets what that means better than what I know what that means.
I'm sure we have a video on it. So it's an example of creating a 5-qubit highly entangled state. State 0, 0, 0, 0, 0 plus 1, 1, 1, 1, 1.
Okay, let me see if. Oh yeah, I can print a nice sample of this. Let me check it out.
Okay, and while Luciano figures that out, I'll answer Eloise's question. Eloise is asking, are there research areas in quantum computer that can be tackled with chemistry, or areas where quantum tech chemistry is the most valuable? So I think the answer is related to one of quantum simulation. quantum computers obey, quantum mechanics, and chemicals, molecules obey quantum mechanics too. So it's very easy to map chemical problems to quantum computers, and we think that is one of the areas where quantum simulation of molecules will be very successful because they have a very similar type of structure. And now Luciano has brought up the device map of fake bubbling again. Can you show me how to do that? Because I always forget how to do that as well.
Yeah, sure. You can import the Jupyter tools, and then with this magic, it's literally called magic in Jupyter Labs, you can have this nice representation of a backend. So in this case, you have this, all these error and even in which frequency they work, and even the job history. I guess this will show my job history. Okay, it's empty. That's good. Yeah, and here is what we mentioned before, the basis gates. And yeah, other information, like for example, how many shots you can do there. Yeah, what is the maximum amount of experiments that you can send?
Oh, this is an older device. I should point out that this device is no longer active or deployed.
No, that's what I wrote it from fake. Yes, yes.
The U gates, which are essentially parameterized single qubit rotations. But they break down into square root of x and RZ gates, which is what we use now.
Yeah, we can do it with a real device now. Any device in particular that you're interested in?
I was using Auckland yesterday, but I had a reservation.
Oh, and it's just to show the map, so we can do that.
Yeah,
what is the name again?
I was using fake Mumbai when I was
Mumbai.
Yeah, MUMBAI.
MU?
MBAI. AI.
AI.
Spelling is neither of our strong suits. MUMBAI. Switch the last bit.
BA.
MUMBAI. Yeah, there we go. Or maybe it's IBMQ Mumbai.
Maybe it's IBMQ, yeah.
It could be IBMQ Mumbai.
Let's do
There's definitely an M there. We've got to put the M back. MUM.
Okay. Manila, Oslo.
Yeah, pick something you can spell.
I don't have access there. Okay.
I was using the fake one anyway.
Get backend.
Yeah,
and we can
why not?
We can do this one, and then you can see the nice snippet for this one. Here, as you said, the arbitrary rotations are not there.
Right.
Because this is one of the new ones, right?
Exactly.
And
but basically there's arbitrary. Yeah, the U1 is the same as an RZ, the U2 is an RZ and SX and RZ, and the U3 is an RZ and SX, RZ, SX, RZ.
Exactly.
It's based on something called Euler angle decompositions, which you probably don't need to worry about. So we could probably talk about.
And now we can transpile our circuit. What was the name of the circuit?
Remember.
Which is it? To backend. And we can draw it. And let's draw it with map.lib because it looks nicer. Yeah, and here we have it. Yeah, here you can see a swap gate here in the top, that also you mentioned before. This sequence of 3 CNOTs.
So what you can see, if you look at the circuit, and if you're used to looking at circuits like Luciano and I, you see these 3 CNOTs in that pattern up there. That is a swap.
Mm-hmm.
So that is exactly the corresponding CNOT definition of swapping the quantum information around. And you see another one to the lower right. And these are pretty expensive because each slot consists of 3 CNOTs. And the CNOT error, I mean, it's getting better as we make better and better devices, but it's typically going to be about 0.5% error per CNOT. So those can add up.
Yep. I mean, we can see explicitly swap maybe with that. No, I don't know what I did wrong here. Oh no,
And
here I
you can
think maybe
see,
we found a better layout. That's why no swap was needed. No, I don't think so. Oh no, because the coupling map is missing now. Okay, the
yeah, yeah,
coupling map
yeah.
is this graph. Yeah.
So it's all this information is inside of that backend properties, and you can extract them if you want to, but a lot of times it's easier to just give to the transpiler and let
Just give the
Qiskit
backend. Yeah.
take the information to. It's like
Mhm.
a backend dot configuration dot qubit coupling map. It's really, really long.
Backend configuration coupling map. Here is a list of the edge in that graph.
Yeah, I
And
remember
they're
because I had to pull
symmetric.
that today because I picked my initial guess of qubits was bad, and I needed another set.
Oh, you fix your initial set of qubits, you said?
Yeah, I mean I
Okay.
had to because um, for this you can put an initial layout. So actually this is a pretty small device, so it's not as interesting to do different mappings.
Oops.
But one thing I did want to point out is notice that qubit 0 goes to qubit 5. The transpiler kind of knows that you want to start with a Hadamard on the circuit that's kind of in the middle of the system so that you can spread the entanglement out from there instead of doing a bunch of swaps later on.
Yeah, here I think it's a good illustration of what you just mentioned, like a non-intelligent. I just put random initial layout that made this map, and a non-intelligent of that selection insert a lot of swaps, a lot of C nodes that you mentioned. They are super expensive. That's why, yeah, you had to be very careful when you choose your initial layout, or you just gotta let the transpiler try to choose the best one for you.
Yeah, and here I'll advertise, if you want to go through the methods of how you would systematically pick the best qubits and do the best swap mapping and et cetera, the most recent season of Nick Knows is all about the techniques I would use to do the same thing.
Nice plug.
Thanks. I'm sure we can drop that in the chat here.
Shall we jump to the next section? Or oh yeah, gate
Yeah.
optimization is important. Yeah.
Right. So gate optimization is going to do a number of things, such as I know that any single qubit rotation can be specified by one of those U3 gates. And one of those U3 gates is going to consist of at most two SX gates. The SX gates are the ones that are physically performed. Those are the square root of x, the 90-degree rotations in the x-axis. The RZ gates are done by frame changes. They are actually not performed, so those come for free. So you don't really care about those existing. So what that means is between any two entangling gates, you should have at most two actual physical single qubit gates. So I would count those SXs and simplify those single qubit gates as much as necessary. There are other things such as if you have two CNOTs in a row, they cancel each other because they just undo each other. So you just want to throw those away. You don't actually want to do them. These are the ones you have to do because these are swaps. But if they're acting in the same direction, then you can eliminate them. And I think I have an example of CX cancellation is one of the steps I go through later.
Oh, okay. Sorry. We don't have to go.
Those are kind of my favorite clean up the circuit kinds of ones is optimize one qubit, optimize one qubit gates and CX cancellation.
Yeah. Another thing that I think is important that is mentioned for optimization is the optimization level that you can pass to the transpiler. Are you familiar with this option?
I am.
So I know that you are. Yeah, I was just trying to give you a prompt.
Yeah. So tell us about the optimization level, Luciano.
Yeah, the optimization level 0. Well, there are 4 levels of optimization: 0, 1, 2, 3, and they're kind of like inspiring the GCC optimization levels, where 0 does no optimization at all, and maybe you can even like see like you can check it out the depth that this required, and you have optimization level 1. You can see there's some optimization being done here. Optimization level 2, and it seems like 9 is the maximum. And yeah, seems like here.
Minimum.
Sorry, the minimum. Sorry, the maximum part that you can optimize. Yes, but yeah, the minimum amount of gates. Oh, here, for example, end up in 10. So this is a good segue to the next feature that I just mentioned. That transpile is a stochastic process. So it's if you run it several times, you may get different results. And And if you want to guarantee that you will have the same result, which is something that many times researchers want to do because they want reproducible results, they need to define a seed for the random number generator in this way.
Yeah.
So in this way,
I usually use 1, 2, 3, 4, 5 because that's the combination of my luggage.
Now the internet knows the combination of your luggage, Nick.
Also, one thing I'll do is
choice.
I will transpile several times. So I will multiply that GHZ circuit as an array and, like, say, create an array of the same circuit 20 times. And then
I see.
the minimum one, but I will still do it with the seed so I can reproduce the minimum in the same way.
I see.
You
In the same process.
The array around. Oh no, you can do it. You can pass the list to the transpiler. You don't have to do the for loop, I think.
I see. But then how you keep, then how you know which seed? Oh, if you keep a seed here, you also will get the same thing.
Oh no. You can put that you can put the square brackets around the circuit, the GHZ, and then I just do times 10 or times 20.
And how you know which seed was using?
Then you can save the output of those as an array of circuits you get back, and then you can count the
okay. So in that case, I think in that case my solution is better because now you can know that 3 is a good one.
Yes. It's a nice demonstration of the stochasticity. and really these are stochastic because, you might wonder, mapping abstract quantum circuits to physical hardware is actually an NP hard problem. So we have to do some heuristic stochastic circuits to kind of get the best solution that we can in a reasonable amount of time.
Yep.
And I would also maybe say that these transpiler passes have all been recently rewritten in Rust. So the performance has increased quite a bit with the recent stable releases of Qiskit, which is nice.
Yeah, many of the critical passes, they have been rewritten in Rust, and we're looking for also migrate other passes. So if you want to learn Rust or you're Rust enthusiastic, jump into the GitHub repo and join us with that.
Yeah, let's carry on, I guess.
So the transpiler is actually some sort of like a wrap function on something that is called a pass manager, which is a bit of a lower level functionality, but that allows kind of like a advanced usage of the transpiler. You can create those pass managers with generate preset pass managers. The preset pass managers refer to these different levels, 0, 1, 2, and 3. And this can be used to create a pass manager, which is actually what it runs inside the transpile function. So for example, this one. And with draw, you can see the full list of passes that they're going to be run in level 1 in this nice graph. Maybe with the backend, so you also have routing. So it's very hard to see this graph, but let me open in a new tab so you can see it. Oh, it's getting bigger and bigger.
Oh wow!
So all those things happen in the behind the scenes when you run transpile. So let's start from the top. Can I? Oh yeah, I can. So first, there are some unitary synthesis. Then there is a high level synthesis. Then unroll, which is one of the passes that you mentioned before. And yeah, all these squares are passes, and some of them are in a what is called a flow control. For example, this one is under a certain condition that will run or not, and that condition will be based on if you are providing a layout or not. So if you give an initial layout, set layout will run, and this full section will be skipped.
Nice. So I may add here that one of the nice things that was learned about quantum computers in the late 90s, I think, is that any arbitrary quantum information can be broken down into single and 2-qubit gates. So that's basically where the transpiler is going.
So we also have this path, for example, which is enlarged with ancillas, which is the one that creates this ancillas output in our example before. I don't have it anymore, but yeah, your abstract circuit may be smaller than the physical one, so we had to enlarge it for that, and that's what this path does, for example, enlarge with ancillas.
Right. So you can use these ancilla or auxiliary, or they have a lot of different names, but resource qubits for trying to do things more efficiently, even if they're not a part of your quantum program. So they were used for swaps, for example.
Yep. And more passes. Here is, for example, the basis translation. Here we have the optimization that runs in a loop, searching for a fixed point, either in depth or in size.
Right. You'll see this is where you're cleaning up a lot of things, like I mentioned optimize 1Q gates decomposition and CX cancellation. That's ones that I like to always use to clean up things.
Yeah, this one is the one that I mentioned. Yeah. And the passes are divided in two sets: the blue squares and the red squares. The blue squares are what we call transformation passes, which basically the things that they really change the circuit, while the red squares are analysis passes that basically they extract some information out of the circuit. For example, in this case, the depth or the basis of that circuit.
Right, and you can use that depth as, say, the cost function for your flow controller.
Yeah, it's the same code that runs when you write. When here we run .depth, that's exactly the same one. Yeah. Okay.
Cool. So we want to go maybe into the stage pass manager, because this is kind of the new feature we wanted to highlight. I think this is the first kind of new recent thing.
Definitely, yes. Because actually, I told you that behind the scenes, a pass manager was running, but what it really runs is a stage pass manager. So if you check the type of this thingy, you would say that it's a stage pass manager. And what it means that it's a stage pass manager? Well, mostly means that you have something that we call stages. And these stages are very handy because they are some sort of like a very high level stage in the transpilation pipeline that you can manipulate. So, for example, we have the stages that Nick mentioned before, right? Well, init is basically the initial things. Layout is the selection of the initial layout. Routing is when the swaps are being inserting. Translation is when we convert some gates into a different basis. Optimization is when we remove some gates because they're redundant or something like that. And scheduling, what is scheduling, Nick?
Oh, that's a great question. So the scheduling comes into play because each of these quantum operations takes a certain amount of time. So you'll actually find, well, we'll probably look at the schedule later, but all the single qubit gates have the same time typically, and all the 2 qubit gates have different times. Other things you might want to do is you'll have idle time between operations because not all the gates commute with each other, so you can't do them out of order. You might have to wait for one to happen before the other one. So you might want to push all your gates to be as late as possible, and that way your qubits are less affected by decoherence. Another thing is you'll have idle times that appear in these circuits no matter what you do, and they a lot of times depend on the type of circuit you're running. You might want to add things such as dynamical decoupling to your idle time to keep your qubits busy. That's kind of the idea. Keep your qubits busy so that they're less prone to dephasing. But typically, it's the last pass for superconducting qubits. It doesn't have to be that way because a lot of times you might want to think about doing layered structures and kind of scheduling your circuit into blocks of single qubit gates and 2 qubit gates, for example. So I think what's great about the stage pass manager is it lets you kind of take all your passes that correspond to one thing and put them in each stage, and then execute the stages as how you're desired. For example, like I like to do routing before layout, for example, because that's
I'm not sure if you will be able to do that though, but yeah, I mean, definitely you can try.
Yeah, exactly.
Yeah, and especially for researchers, if you are focusing on a specific stage and you don't care about the rest, let's say that you are doing research in a specific way of optimizing your circuit, but you don't care about how it's being wrote. In that case, you can only change that element and take the rest as default if you want. And each of these stages is a path manager themselves. That's why you also can draw them, and that's why you will get this nice graph after that. If you remember correctly, from the big path manager, this one is only that stage. This was the last part of that one.
Yeah, it's a lot easier to take off these smaller bites of the transpiler and deal with those separately.
Yeah. And something else that you like to mention about stage path manager? I mean, all these stages, you can manipulate them.
Yeah, I think we just wanted to try to manipulate one. If we could, I think what I was telling you was if we look at the initialization stage of transpiler level 3, you can find some passes that do some swap mapping that don't necessarily preserve unitarity by switching, eliminating swaps by moving the qubit ordering around and the measurements around to try to get rid of swaps, which is usually a good thing. But sometimes if you break unitary equivalence, then you are not actually doing the same quantum operation you might think you're doing.
Yeah. Well, the routing happens. I mean, if you check the routing pass, you will see routing stage. Sorry, you will see there is something going on. But if you don't give a backend, this full stage is being skipped automatically.
Oh, I think it was the init stage actually.
Okay, in the init stage there is something that I would like to remove. Okay, let's check it out.
In level 3 optimization.
Oh, level 3. Okay. We changed level 3 in the
but
top.
I think it wasn't in level 2.
I changed it to level 3 here.
Okay, gotcha.
Oh, okay, so much happening in level 3 initialization.
Yeah, let's take a look at a couple of those.
Let me
so
see
I think there were 2 of them that I didn't like, and I wanted to try to remove them.
Okay, fair enough. Which ones you don't like?
Remove reset in Z. I don't know if that's that bad one.
Remove reset in 0 state. This one.
Yeah. No, I don't know.
Oh, we can remove this one just for the illustration.
No, I'm going to take that back because if you're doing a reset, then you're not doing a unitary operation anyway, so that one doesn't matter. But I think it's optimize swap before measure and the remove diagonal gates before measurements, because those will change the actual unitary of the quantum operation you're doing in ways that make it maybe harder if you want to use this as a piece to go into another circuit. It's usually good if you're just executing the circuit alone, but a lot of times you want to build a circuit and then build a larger circuit out of it, in which case you don't want these things.
Yeah, let's illustrate what these passes do with an example, if you don't mind.
That sounds great. No, please. I think this will be very instructive.
So we need to so the pass that we're going to analyze is optimize swap before measurement. So I guess we're gonna need swaps. So we can do a QC.
If you do the remove diagonal gates, it might be easier to see, actually, because we can do it on less qubits.
But I have no idea what a diagonal gate is. What is a diagonal gate, Nick?
An RZ, a Z rotation. Basically, what happens is if you do a Z rotation and then you measure the qubit, the Z rotation doesn't change the measurement of the Z basis because you're going around, so it doesn't affect the measurement results.
What did I do wrong? Oh yeah, I need an angle.
Yeah. So.
Yes. What is the angle that I should give?
0.5 pi over 3. Yeah, pi over 3. I don't know.
Pi over 3. Perfect.
Yeah.
Okay.
There you go.
Here's our gate. And remove before measurement will remove this one, right?
Yep. We should remove both of them.
Okay. So I think it could be also a good example to illustrate that you can call passes as functions. So if you import your pass, you can initiate it and keep it somewhere. And then you can call it with your QC. Oh, nothing happened. Is this a real diagonal thingy?
Yeah.
Maybe it's called later.
Wait, don't you have to run the pass manager to get it to do something? Does that run it?
Yeah, that runs the pass.
Similar. Okay.
That runs the pass, but maybe we're missing something before. I don't know. Let me see if I can run the other one, the optimization swap before measurement. And for that, we need to QC swap 0, 1, and then we have to measure all. Okay, here there is a swap in front of the measurements. And let's see if I can optimize that.
Oh, maybe there was no measurement on that one. I think that's why I didn't remove it.
Ah, that's why. Okay, that could be. Let's check it out. Wait, what's going on? Oh, this is in a different place.
Yeah, I think some of these, you can get them from passes. I think you can definitely import them from a higher level in the directory.
Still not working though. What we are doing wrong? Optimize before pass QC draw. Okay, let's build it as in the pass manager as you suggested before. From Qiskit Transpiler import. Can I? No. Oh yeah, pass manager. Perfect. And here we put it in a pass manager.
Yeah, this is usually how I do it.
Okay, perfect. PM run, pass manager run, and QC, and now we draw the result. Still there.
Maybe the barriers need to be removed before.
The barriers. That's a good one. That's a good one. Yeah. 0, 0. Because measure all insert that barrier. So let's see if we can remove the barrier. Oops. What's going on now? Measure.
There's no classical register in the circuit.
Good point. Perfect. Now let's see. There's a parenthesis wrong. And now we can run it. Yay! Okay, now I still want to run my pass manager as a function because that was my selling point, but let me see if I can do it. And then we can move on. Otherwise, it will stuck in my mind. The full week.
Yeah, watch as two transpiler experts mess with a transpiler together.
Yeah, exactly. Yeah. It worked. So QC was with a swap, and here the swap was removed, and the measurement was swapped.
Yeah, and now I wonder if getting rid of optimize or remove diagonal gates before measurement will get rid of the RZs as well.
We can check it out. Remove diagonals before measurement.
So I think you want to do that after in the pass manager after the optimize swap, because it got rid of that one first.
Sounds good. Yeah. Something like this. This is getting tricky.
Yeah.
Yay!
There you go.
Yeah. But in this case, for example, once that you run 2 passes, makes much more sense to build your own pass manager, as you suggested before, right? You run first the pass manager with with optimize swap before, and then you run the remove diagonal.
Yeah, I'm often building a list of passes and creating my own pass manager. Exactly.
I'm doing it here in the nested way, but it's probably better practice instead of doing so much inlining. So yeah, our quantum circuit, now we can pass manager.run. We run our pass manager on our quantum circuit, and that gives us a none thing. So going back to our original goal, your goal is to remove these 2 passes out of the initial stage of the level 3 of the preset pass manager. It was a very long sentence, but it was correct. Okay.
So you'll see that the the quantum operation that we're doing here is the identity matrix because we're doing nothing and we're measuring. But the quantum operation of doing the RZs and the swaps is not the identity. So those things are not equal to each other. So if you try to pass certain circuits through things that break unitary equivalence, you can end up not getting the circuit you desire. Depending on what you're doing, of course.
Yeah, of course, yes. What was the name of the way to get the generate?
Init.
Generate. Yeah, and then here we're going to have the init, and let's list the passes. Perfect. And the simplest way to do that is by messing up in this structure, which is basically a list of very small pass managers that they run in a line. So so if you get you can get one by one in this way, but here we're going to get rid of which ones? These two.
I think the last two.
Yeah. Okay. So -1 is our remove diagonal gates. I think you can definitely remove like this, like del, and that will work. But let me first graph that this works as we expect it works, right? If we run this stage pass manager init run with our original circuit, we get again the identity as you said. And now let's remove the last pass. Oops. Okay.
So is this the best method to delete the element of the list?
It's a very Python way to do that. Yes. Actually, it's still there, right? It's still there though.
Oh, because this is being returned from a function call.
Ah, I see. Mm-hmm. Okay. Mm-hmm. Do we have a way to remove?
So there's probably some internal way to remove them.
Oh, remove is a method indeed. So let me see what is the removes a particular pass in the scheduler. Oh, there we have.
Yeah. And it's probably better to use the
yes, the constructions that they are provided. Yeah.
That's what I wanted to say. Thank
you. Yep. I guess I have to give the full.
Oh, I thought
what is it?
I thought it was on the position. I thought you could give it -1 and it would work.
But okay.
We'll find out.
Remove -1. That's it.
Yeah.
Oh, that's good.
Boom.
Let's see if that remove it. Yep, it's not there anymore. Yep. So let's remove another one.
Yep.
Up. And it's
Gonzo.
Gonzo. Yes, perfect. And now let's run again our. And there they have. Yes.
And now you have unitary equivalence.
Yes, it's a. We are trying to have an option in the transpiler to see if you want to preserve the unitary equivalence, right? Because what would we preserve? I'm not sure if this is a real name, but it's. I think we can call it observability equivalence. Basically, what you get to read is the same, right? Because what you read will be the same if you remove everything and you get the identity. You will get 0, 0, right?
That's right. Okay, so I'm just noticing we have 15 minutes. Do you want to go through building the pass manager example like I was talking about, or do you want to go through debugging, or maybe we can do both at the same time?
Yeah, both at the same time sounds challenging. So let's go. Yeah, you sent me a notebook yesterday that you want to go through. Shall I bring it up or?
Yeah, why don't we go through line by line and I can kind of tell you what we're doing, because this applies to a lot of classes of circuits, and so people might be interested in this.
It's also Greek for me, so I'm curious to see what that's do. Yeah.
Okay. So yeah, just import, like, I guess you can run the first two cells.
Mm-hmm.
Okay, you're just going to run it here. Okay, so basically what we're doing is we're importing a type of circuit called toLocal.
And what is toLocal?
Okay, so toLocal is basically, what toLocal does is it helps you build an Ansatz. And Ansatz is a fancy German word for guess. Is that right? You speak some German, right, Luciano?
Meine Deutsch ist kaputt.
Okay, so Ansatz, I think of it as a fancy German word for guess, and usually it'll be a parameterized guess, and you will use it as an you will use an optimizer to perfect those guesses that you're using, or you can use it to encode feature spaces for quantum machine learning, for example. But usually it's a structure of circuit that has a bunch of single qubit gates separated by entanglers. You can't really see it here, but you could do probably a decompose or two on that QC to see that in this construction, I use the RX and RZ gates as the single qubit gates and the RZZ as the entangling gate. So not the C naught. So this is just a choice. It's a choice that might be useful for chemistry, for example, because ZZs are particle conserving instead of using C naughts, which are not particle conserving because they create excitations and stuff. So depending on what your application is, this toLocal function can generate a type of circuit that's very useful for you in, say, a VQE or QML or QAOA type of algorithm. So that's all I wanted to say about that. I was just basically trying to get a structure out of it. And what I'm going to do is transpile it to a backend. So I'll use fake Mumbai here, and we can draw that circuit as well. And now we're converting that because the ZZ operations are not basis gate operations. So what the transpiler is going to do is going to take these ZZs, which are a function of parameters, theta, and it's going to convert them into something that's unitary equivalent, which is going to be a C naught, an RZ, and another C naught. So that's just a different way of expressing the ZZ. These are unitarily equivalent. I'm a very big fan of unitary equivalence. And you can see now that the angle has been mapped onto the single qubit gate, this RZ gate, which actually does not actually occur. It does done by a virtual Z in software. And so one of the things that has been part of my research over the past couple of years is better ways of representing these types of interactions, knowing that at the pulse level, the way that we build up our C naught gates is equivalent to something called a ZX interaction. And you can build a ZZ out of a ZX interaction. So this is basically transpiler passes that will do that. We've added this capability into Qiskit. And so what I would do here, so I import some transpiler passes. I'm going to get all of the backend information that I need for those transpiler passes. So normally you would put it in the backend. So yeah, we're going to use template optimization. That's the fancy one. Then I'll clean things up with optimize 1 qubit gates, decomposition, and CX cancellation, and then do the pull stuff with RZX calibration builders. So let's go through kind of these one at a time. So the basis gates, we can get basis gates from configuration. Just put the backend in there, and the transpiler pass knows how to get it back out. For certain reasons, we try to just pass not the whole backend to these specialized transpiler passes. We also have something called the instruction schedule map. What the instruction schedule map does on the next line is it takes all of those instructions that are possible, essentially every basis gate for every qubit, and it puts it in the instruction schedule map, and it tells it the pulse schedule to do corresponding to that actual gate. So the instruction schedule map is basically the translation between a quantum gate and a pulse schedule, which gives you the kind of actual physical microwave operation you need to implement that quantum gate.
And this will be useful in the schedule stage that we saw before.
Yes, and it will also be used in the schedule space because it has all the timing information of all the pulses as well. And then the next one is the channel map, which tells you which qubits are coupled to each other because of the finite connectivity. We need to know which ones we can actually execute 2 qubit gates between. So these are kind of like the very, very device level details that like a physicist like me would really appreciate having the knowledge of. These are all available via these kinds of methods. You can find them in backend.configuration, backend.defaults, and backend.properties. There's a wealth of information about backends in there. And you can do them on real devices or the fake devices as I did here, just for, so everyone can do it. So what we're going to do is construct a pass manager. We're going to use 2 areas of research. In fact, if you go into a lot of these advanced passes, they are actually research projects that became folded into Qiskit and became a part of what researchers started messing around with. And then they merged it into Qiskit so that all Qiskit users have the ability to do that now. So that's what I'm going to show you. So this first one's called template optimization. This was from your colleagues in Zurich, a novel template optimization technique for converting structures of those C naughts and RZ C naughts into something more native like these RZX. So basically what the template is it's a pattern of gates like a C naught, an RZ, a C naught, and some single and some other cubic gates. And what the template optimization tries to do is it searches the circuit for this certain pattern, and it can replace it with its inverse because the template itself is equal to the identity. The inverse would be equal to the other part. And then it asks the cost function if one of these things is cheaper than the other one. So basically the way I know this works is it's going to look for that C naught, RZ C naught. It's going to be like, I know that's a ZZ, and I know I can represent that easier with a ZX rotation, which I can implement easy at the pulse level. So that's basically what that does. It's a analysis pass that replaces these things. Well, or maybe it is a transformation pass because it does transform the gates, but it preserves unitary equivalence.
I was checking here in the it's a transformation pass. It's subclass in transformation pass.
Okay, yeah. So it's because it changes the gates that you're doing, but it preserves unitary equivalence. So that's what it's going to do. It's a way to analyze the circuit so that we can hope to replace it with pulses that do the same thing but more efficiently. And so then we go through, and the next one is optimize 1-2 gates decomposition. This cleans up your single cubic gates. You've got to feed it the basis gates, which I got from the backend configuration.
Yeah, this one is quite standard. It's used in the preset pass managers.
I always throw these two in there. CX cancellation, kind of do these back to back. Like when I'm doing my fancy things, research-wise, I threw these passes in between to clean things up between them. So then the next fancy thing is the last pass, which is the RZX calibration builder, which is a piece of research I worked on with also some of your colleagues, with one of your colleagues in Zurich as well. And what this does is it analyzes those where the RZX pulses are, and those pulses are actually still parameterized. It can take the parameters of these arbitrary angles, and it will ask the instruction schedule map, what is the C naught corresponding to that pair of qubits, and it will transform the pulses corresponding to that C naught to give you an RZX gate. That gives you actually the pulse schedule for an RZX gate, and it will attach it back to the gate as a pulse gate. So in fact, what it does is it does all this pulse level stuff, but it doesn't tell you anything about it. It replaces it with a V gate. So you don't need to know anything that's really happening under the hood. You just kind of need to know that that's how it works. Or you need to know that that's what it does, and then you don't have to think about it anymore. So now that, it was a piece of research that I did a couple of years ago, but now I just use it all the time and I don't think about it because I know what's happening under the hood. So what we can do is examine this right now. So what we're going to do is I'm going to run this pass manager on my quantum circuit, and I'm going to attach a bunch of random parameters to it, and then do this output this as a QC scaled. That's what the S stands for, and we can look at that circuit and see what happens.
Yeah, this assigned parameters replaces those thetas that we have originally by, in this case, random numbers.
Right, there's random numbers, but these are, say, for a VQE algorithm, these are the parameters that you would want to optimize using, say, sort of stochastic optimizer or something. So this is how you kind of interact between the circuits and the parameters. And so when you look at the circuit, you'll see two things. You'll see that those C naughts and RZ C naughts have been replaced by these RZXs. You'll see those RZXs now have a number between them because that is the arbitrary parameter that was then bound to that circuit. And you'll see this cal underneath the RZX, which means that a pulse gate has been attached to that, which means now the backend doesn't know what an RZX gate is because it's not in the basis gate set. But because I've attached a pulse schedule to it, it knows what to do. And so it won't complain when you try to send this to a backend now, because you provided it with the instructions it needs to know in lieu of it already being in the basis gate set.
So what we can do here is abstraction lower. It's at these boxes defined at pulse level, but even if I don't know what that means at higher level, I know how to implement this pulse, and that's why the backend will accept it.
Right, and because we physics people like me know how to manipulate these pulses on an individual level. Most people don't want to do that, and once we figure out what to do, we don't want to look at it individually either. We just want to do it. So this just does it, and you don't have to worry about it. But we can look at it and see what actually happened by scheduling, which converts the circuit into a pulse schedule. So you can see all the microwave pulses that's happening, and that's what we can do just to show as an example here. So basically what I'm going to tell you here, we have two channels, which are, there's the D channels, which are the drive channels, where there's single qubit gates. They're represented by blue pulses. And we have the U channels, which are control channels, which are represented by 2 qubit gates across resonance pulses. So that's a little further down. And you can see these yellow ones, and you can see that they're very different in size. They're usually different in size depending on the gates, but what this doing is it's changing them based on the parameters. So you can see the second one had a much smaller parameter if you look up at the circuit, because it's much smaller than the other one on the left. And basically the way I think about it is these 2 qubit operations are where most of the error is being introduced. So you kind of want to minimize these by scaling them down as much as you can. And so what we could do is the next line will execute the same scheduling, but to the circuit that we didn't do the pulse scaling on. And so before you go down, Luciano, can you look at the cycle time? So the time the circuit takes is 5,500 DTs. Oh, it's
5,200.
Yeah, 5,200. Now we can go down to the next one, and we can see what the cycle time is there, 10,700. So you're already doing something by doing pulse scaling. You're executing the circuit in half the amount of time that you would if you didn't scale it. And if you look down, you can see the yellow pulses are going to be a lot bigger, because a lot more of them, because you didn't efficiently do your ZZ gates in terms of ZX gates here. You actually did this digital decomposition into C naught, RZ, C naughts. So you can see each one of those C naughts consists of 2 of these yellow pulses because of something built out of Ecker cross resonance, which means it has 1 plus and 1 minus. And then you can see there's a virtual Z where no gate was actually done, but it's given by this little
loopy.
Yeah, I don't even know what you call that.
Yeah,
followed by another C naught.
A repeat icon. Yeah.
It's just to indicate that this operation is happening, but it doesn't take any time. So that's it uses this symbol to represent it. But basically what you'll find is when you try to execute the second way without the scaling, you'll incur a lot more error versus the first way. So this is something that we've been working on research on. I had an intern who did this kind of work with variational algorithms. So very, very close to what you're doing, but using the transpiler to figure out more and better ways of kind of squeezing your circuit down in the number of gates or number of pulses and amount of time is a lot of what the research in the transpiler is there for.
Gotcha. Okay.
And then I don't know if you want to try and just do the last example of a plugin. Maybe we could just do the token thing.
The token thing. Sorry. Sorry,
So
what do you mean by
the plugin Qiskit-token?
Oh yes, well, each stages you can write your own things, your own passes for that. But I'm not sure if what you wrote here will be a single stage or several though. What you wrote here seems to me that this part will belong to the schedule stage, while this part probably will belong to the optimization stage.
Yeah, that's actually a great point, is that some of these aren't very well defined in what we're doing here. I probably would separate these if I was to make a general kind of thing, because you're right, the first one has nothing to do with scheduling, but the second one does. Actually, you know what? Because it's a pulse gate, I think you can schedule after this. I think you can do these all at once. I'm going to take what I said back. Because it's a pulse gate, so it hasn't been scheduled. It's just attached the information to the gate.
I see.
So that it knows how to schedule.
So you could add this your custom pass manager as part of the station system. You can add it in the, so each stage has its own. It has two implicit stages, which is the pre and the post. So this one you could add it to the post optimization one, and that will run in a loop to reduce the depth. However, it seems to me that you're optimizing by duration and that's not the default fixed point for the optimization loop. Because again, it's not scheduled yet. That's why I would like to put this one in the scheduled part. But it's a bit up to you. We could try to play with it and see what we can do. So in the previous stage pass manager, you could, for example, add your pass manager from before. You could add it to SPM post optimization.
Optimization, probably.
Yeah, and then if you do this, that will add these stages in your after optimization, right? So we can let me copy the full cell. I'm not sure if this will work, but we can try.
I'll go out with a bang.
And then we can add it in the post optimization. Right, and then we can run the same stage path manager with the quantum circuit that you define, which is this one. Let's also bind the parameters already now, so we don't have to worry about that later.
I did it in the, it's all in one line.
Yeah. We can call this one QC bind it. No, bind is the pass, right? My English is also.
No, I use.
Perfect.
Yeah, that should be good.
Qt is not defined. Because
you got to transpile to the basis.
Oh, you transpiled it before. Okay, I think we can do that directly, like this. Let me see what happened. Qt again is not defined.
It's also looking at the number of parameters. Yeah, you can use QC there.
Perfect. So you don't have to transpile it before. It's okay. You can do it like this. And now we can run our state patch manager with the post optimization that you define, and with QC bind. And we can save this one as final. And then let's see what is the schedule. Well, how did you define the schedule before? Oh, basically you just schedule that.
Yeah, why don't you see?
But I do it with a different backend though. Well, I'm not sure if that will work.
Yeah, just see if the.
Which backend have been using here?
Figma by.
Nairobi, I'm using here.
Oh.
Oops. Oh, yeah.
Yeah, I don't think it attached the pulse gates because I'm afraid that when you tried to assign parameters or when you tried to run it through there, it didn't transpile the abstract circuit into the basis gates. Because it doesn't know what the basis gates are.
Oh, I see. Yes, I need to keep a backend here, of course. Like this, right? Let me see.
I think so.
It didn't work, no. Because the RC is running too late somehow.
Can you see what the output is of the QC bind?
QC, you mean this one?
No, the one previous one, bind.
Bind. Okay. What should I check here?
Just draw it.
Oh.
Yeah, see, it's still this two locals circuit. It hasn't been converted into any kind of gate. It's still a two local.
Oh, okay. How can I decompose it?
I think you can probably put decompose maybe once or twice. It's always, I never know what decompose is going to do.
Let's check it out. Nope, still not working though. And that's in our set. So I think that's not the problem. Operational set. It's not supported.
Oh yeah, so RZZ, it hasn't been still translated to RZXs yet, so it doesn't know what to do.
Okay, so it seems to me that after our stage, we need to decompose again to the backend.
Yeah, Maybe
Right.
another decompose will fix that.
No, I don't think that will, right? Because the RCC are inserted by your pass.
Yep.
So I don't think that this will have any effect. We can check it out, but
There we go. I was right.
I will shut up. Yep.
Indicated.
Oh, look at that!
Okay.
4,000, even faster than before.
Yeah.
But it could be because it's a
Well,
backend.
it's a different
Yeah.
backend. So I think we're a little over, but I think that's a great way to go out on. We're having a lot of fun today with the Qiskit Transpiler. Maybe a little bit too much fun, but we hope you showed you the kind of flexibility and circuit improvements that quantum researchers and developers are still working to implement with these quantum circuits. And I'd like to say it's been a great time being the host and sharing the stage with Luciano today and previous ones. And I'd like to thank all of our previous Qiskitters for hosting these wonderful 12 days of Qiskit sessions. And thanks to the audience for all the wonderful questions and your attention. And then I think I'd like to go out with a last note. I want everyone to have a happy holiday and tune in for our final 12th day of Qiskit tomorrow. We'll have the premiere of our Qiskit Roundtable with all the Qiskit hosts, premiering at noon Eastern Standard Time tomorrow. Any last words, Luciano?
No, I think this was a nice trip. I mean, we wanted the days to go increasing in difficulty, and I think this one was kind of like it gives some food for those experts out there that want to dive into a transpiler, and it was great to host this with you, Nick, as always. And yeah, really looking forward to tomorrow's roundtable.
Yep, great. Thank you so much, and I hope you enjoy all the snow you're having in Zurich.
We have some snow here. It was the first snow of the year. I hope that in Colombia you don't have snow. Otherwise, there is something wrong with the climate. Well, it is something wrong with the climate.
Okay. Well, that's great. So thank you for watching, everyone, and we'll see you later, Qiskitters.